This is class review on May 18th, 2020. Today we tried to do a couple of things. First of all, I introduced something called colligative properties. And the second thing that we talked about was something called solubility product, or KSP. That's really just another equilibrium constant. All right, so in colligative properties, this is just, I just think you should be exposed to. It's kind of a common everyday chemistry. Colligative properties of solutions are properties that change when you add a solute. So colligative properties. Properties of solutions affected by the solute. And the solute, of course, is what you dissolve in a solution. There are 4 of them. I posted a couple of videos over here that you can see. First one, Introduction to Colligative Properties. We'll just take a little snippet of it. It's a very short video anyway. So take a quick look at that. And
all right, so let's talk about colligative.
The colligative properties are vapor pressure lowers, boiling point rises, freezing point lowers, and osmotic pressure increases. The one that's most common in your everyday life probably that affects you is boiling point and freezing point effect. So for example, when you actually put a solute into a solvent, what happens is the solute expands the liquid range. So if this is normal freezing and boiling, adding a solute would make the boiling point higher, like it might make the boiling point go to 103 or something for water, and maybe this go down to -10 degrees Celsius. So it expands the liquid range, and this is relevant when you put antifreeze in a car radiator. The antifreeze prevents boiling over in the summer. It raises the boiling point so that the engine can be hotter and the coolant will not boil. And in the winter, it keeps the coolant in your car from freezing. So it lowers the freezing point. So if you lower the freezing point to 10 degrees below zero and the temperature outside is 5 degrees below zero, then your radiator won't freeze. But if you hadn't put the antifreeze in, it would. Another place that you see this is in the winter. You put salt on the ice on a sidewalk. The salt lowers the freezing point of the ice. So if the ice is at 0 degrees and you lower the freezing point to -5 degrees, then that -5 is lower than 0, so the ice is going to melt, and that's why you put salt on your ice on your sidewalks in the winter. Or some of you made homemade ice cream before, and putting salt on the ice causes the ice cream to melt, causes this ice to melt. So water in the solid state is going to water in a liquid state, and that requires energy. So energy goes over here. So that means then that the ice cream has to give the energy to make the ice melt, and so the ice cream freezes. So it's just some common applications of colligative properties. Vapor pressure. You could think of vapor pressure as a tendency of something to turn into a vapor, like gasoline has a high vapor pressure and water is not so high. When you put a solute into a solvent, it actually lowers the vapor pressure of the solution, so it makes it even lower. So it makes it harder for it to evaporate, if you will. And osmotic pressure is also affected. We're not going to get into that today, lest I get off on a long discussion. So real quickly, then the rest of this video, you can watch it on your own, but she talks about what they are. And it turns out that the effect on the colligative properties is dependent upon the molality of the solution. And molality is kind of like molarity, except it's moles of solute. And instead of per liter of solution, it's per kilogram of solvent. And there's a little equation that I'll just show you the freezing point one. They all have slightly different equations, but the change in temp, they all meaning vapor pressure, boiling point, and so on. The change in temperature of the freezing point is equal to the molality of the solution multiplied by a constant K, which is like a proportionality constant, times I, where I is the number of particles that are in the solution. So if you look at for example, sodium chloride would break into 2 particles, so the I would be, this I would be 2. Sugar, if you had sugar, it doesn't break apart. It doesn't break apart except that this molecule, let me say that again. These molecules, if I had 100 of these, they'd all 100 separate and become 100 separate molecules. But if I had 100 of these, it would become 100 sodium ions and 100 sodium ions because the formula unit actually splits apart. If you have calcium chloride, that's going to break into 3 pieces because it's going to break into 1 calcium and there'd be 2 chlorides. So that's 3. So the I for this one would be 2. That is I, meaning this I right here, called the Van Hoff factor, would be 2. The I for the calcium chloride, that would be 3, but the I for the sugar would only be 1. All right. So she goes on and talks about that. I'll let you watch the video. And then I put another one on here. This is going through the math. This guy does a nice, concise job of going through the math.
Freezing point depression represents
And
one of our 4
you can see the definitions of the terms and so on here. Mostly I want you to know that when you add a solute to a solvent, you expand the liquid range. All right, the next part of class, I'll let you watch those two. The next part of class dealt with solubility products. So I posted not a very good copy of this, but some practice problems for you to do with solubility product. So the how-to is going to be in this video that I'm making, except there's an example here for the third kind of problem over here, which is the harder of the 3 kinds, or basically 3 kinds of problems you could run into with solubility product. All right, so what is solubility product? Well, it turns out that things that are soluble in water dissolve 100%. Things that are not soluble don't dissolve, but yet they do dissolve a little bit. So even things that are not soluble, like barium sulfate. If you look at solubility rules on your equation help sheet, it'll tell you that barium sulfate's insoluble. But the barium and the sulfate ion do dissolve a little bit and they hit equilibrium. So this is solid. These guys would be aqueous, dissolved in water. And if I set up an equilibrium expression for that, K would equal the barium concentration multiplied by the sulfate. You know, products divided by reactants, that's a -2. All right, and then it would be over the reactants, but the reactant is a solid. And remember, we don't include solids in equilibrium expressions. So really the solid is over here multiplied by the equilibrium constant. And if I take the concentration of this times this equilibrium constant, I get a new constant called KSP, kind of like we did with Ka for acids or Kb. So KSP is the solubility product constant. All right, so 3 kinds of problems. You could be given concentration, find KSP. Or you could be given KSP, find solubility. Or you could predict precipitates. All right, so now let's take a look at one of the first ones up here. How about, we'll do the SRF2 problem. Actually, let's do the lead iodide problem, PbI03-2. I did the first one in class. We'll do this one as another example, a different example. All right, so we have PbI iodate, or lead-2 iodate. It's in solution, and that lead-2 iodate is insoluble. And since it's insoluble, that means there's an equilibrium, and even though it's insoluble, it's not completely insoluble. Let me just show you what I mean by that real quick. So if you remember the equation help sheet, I have this thing called solubility rules on it. Uh-oh. Okay, on the solubility rules, they're over here. Well, it turns out when you really look at the details, and they're not on this page because I didn't bring it up when I put them on this sheet, but to be insoluble, like it says here, like halides are soluble except for silver, mercury 1, and lead, or sulfates are soluble except for barium sulfate. Their little caveat is that insoluble, not soluble, means that less than 3 grams of solute per 100 milliliters of solution will dissolve. So that's 3 grams per 100 milliliters. Well, what if you have 2 grams dissolving? That's insoluble. What if you have 1 gram dissolving? That's insoluble. But yet there's a different degrees of insolubility. Some are more insoluble than others. So that's what I mean when I say even things that are insoluble are not completely insoluble. All right, now I need to find that tab I had open. There it is. Okay, so the lead iodide, it tells us that we have 2.3 milligrams that dissolve per 100 cubic centimeters. So 2.3 milligrams per 100 milliliters. So we're going to need to change our milligram. We're going to need to find the solubility in moles per liter because remember these brackets mean moles per liter. So let's go ahead and do that. Change 2.3 milligrams to moles. So we have 0.0023 grams of lead iodate. Some of these problems are nice because they already give you moles per liter. You don't have to make this conversion I'm doing right now. So when you do your practice, you might just do those because that's that way you won't have to do the conversion that I'm doing in order to get the problem right. And on the little quiz I'm going to make up, I'll go ahead and give you molarities. All right, so we have 0.0023 moles of lead iodate. So lead's 207, and iodine is 127, I believe. Let me just double check that. Iodine, yeah, 127. All right, so we'll go ahead and finish this out. We got lead is 207, iodine is 127, so 127 times 2. And then I'd have oxygen, and there's 16, and it'd be 16 times 6 because there are 2 groups of 3 there. So that equals 557. So 0.0023 divided by 557 equals 4.13 times 10 to the negative 6. Moles divided by 100 milliliters, which is 0.1 liters. So I divide that by 0.1, I do that on the side, and my total solubility would be 4.13 times 10 to the negative 5th. So some of this reacts, X amount, but now we know what X is. X is 4.13 times 10 to the negative 5th. So this is 4.13 times 10 to the negative 5th because that would be X, and this would be, of course, 2X because of the 2-to-1 ratio. So this would actually be 8.26 times 10 to the negative 5th. Now when you set up your expression like we did up here, this time it would be KSP is equal to the concentration of the lead multiplied by the iodate squared because there's a 2 here. So, and in effect I'm kind of using that 2 twice. I had to use it in a 2-to-1 ratio and then it still squares the expression. All right, so I plug in the numbers, 4.13 times 10 to the negative 5th, multiplied by 8.26 times 10 to the negative 5th, squared. So here we go, 4.13, second e negative 5th times 8.26. So you get 2.8 times 10 to the negative 13th. And that would be the solubility product of the lead iodate. Okay, then you'd come back down. This was question number 10. No, question number 6. Look for 6. 2.8 times 10 to the negative 13th. So that's what we got. All right, so that's how you do these practice problems. We'll do one of the other kinds. So that was a given concentration, find KSP. Now we're going to, given KSP, find solubility. So we'll take a look at number, we'll do number 10. Now we'll do number 9. All right, so here's number 9. So you have aluminum hydroxide. Aluminum hydroxide is insoluble, so we're going to do this, aluminum plus 3 hydroxides, and that would be at equilibrium. So at equilibrium, this concentration will be X, because we know X amount of this dissolves, so that's X, and that's 3X this time. So you'd set up your KSP expression. It would just be the concentration of the aluminum multiplied by the hydroxide, whatever that is, cubed. So you know this is x, and this is 3x, but that will be cubed. So you end up with really 27x to the fourth, because 3 cubed is 9. 3 squared is 9, times 3 is 27, so 3 cubed is 27. And then x cubed is x cubed, times x is x to the fourth. And the solubility product, it tells us back over on the other side here, is 1.26 times 10 to the negative 33rd. Now, you need to realize that the smaller the solubility product, the smaller this constant, the less product there is, which means it's less soluble, because product is the stuff that is dissolved. So the smaller the constant, let me write that down, smaller constant, smaller KSP, equals less soluble. So the smaller the number, the less product. All right, so to solve this, then we need to divide by 27 and take the fourth root. So we'd have 1.26 times 10 to the negative 33rd, and we would divide by 27, and then raise that to the 0.25 power, or take the fourth root, so x equals 2.61 times 10 to the negative 9th. And so that would be the solubility, that's what x is, how much dissolves, of the aluminum hydroxide. So we said 2.61 times 10 to the negative 9th. That's number 9, and there's our answer. So we agree. So your answers are down here. All right. Last kind of problem with this, will there be a precipitate? There's an example here explained. I'm going to use a different site for that and just work through one of these problems. We'll just pick a new problem here. All right, so you've got some salt MX2, and you're making the MX2 by doing MnO3 2 plus NaX. And of course, when you mix those together, you're going to get sodium nitrate, and you're going to get M with X. But since X has to have a -1 charge, and M is +2 because nitrate's -1, so this has to be MX2, then you balance the equation like that. What we ask is, will there be a precipitate? You will remember that when we did the precipitation lab, where we had all those equations we had to write back in the fall, and some of the precipitates were harder to see than others. Some were just like they jumped right out at you, like that real bright yellow lead iodide. But there were some that were kind of a faint white, and it's hard to tell if they were a precipitate or not. And that's because of different degrees of insolubility. So what we're going to try and figure out is, will we see a precipitate form, or will it get cloudy? All right, so our KSP expression will be based on the MX2. So MX2, the potential precipitate, would come apart like this, M plus 2X. And that'd be an equilibrium. And if we knew our concentrations of the M and the X, we could plug them in and see if it actually equals the KSP or if it's more or less. So this becomes like a Q problem that we did in the equilibrium unit. All right, so the KSP is equal to the concentration of the M, whatever that is, multiplied by the concentration of the X squared. So now we need to figure out what those concentrations are. Well, over here in the problem, it tells us that we have 0.0014 molar MnO3, 0.0014 molar NO3, whatever, NO32. So when that dissolves, MnO32 turns into M plus 2 NO3 minuses. So since this is a 1-to-1 ratio, whatever this is also the M concentration, 0.0014. And that's soluble because nitrates are soluble. By the same logic, if you have 0.003 molar NaX, but there's only one Na, when NaX dissolves, it's going to turn into Na and X. So that's going to be 0.003 molar. Okay. What makes these problems a little different than other problems of this genre is that you're just throwing this into a bucket. So it's like you got a beaker sitting here, and some just sitting there. You're going to throw this into beaker, and you're going to throw this into beaker. The point I'm making is that the concentration of the X, or the concentration of the M, does not depend upon this actual equilibrium. It just depends on what you throw in the bucket. So you're just throwing some in, see what will happen. So 0.0014, 0.003. However, in this problem it says equal volumes are added. Equal volumes, see right there, equal volumes. So that means that when you put them together, since the volume is going to double, the concentration will cut in half. Once again, the volume doubles, so the concentration will cut in half if you add them together. So instead of using 0.0014 in our equilibrium expression over here, or KSP, we're going to use 0.0007. And the concentration of X will be half of the 0.003, so it'll be 0.0015. If you multiply 0.0015 times 2, you get 0.003. So, and this would have to be squared because of that 2 right there, which is because of that 2 there. Now, but however, you remember before we multiplied whatever the concentration was by 2, but again, you don't need to do that here because we're just taking whatever we threw in the bucket and see what happens. All right, so I worked that out. 0.007 times 0.0015 quantity squared is 1.6, 1.58, or 1.6, we'll call it, times 10 to the negative 9th. Okay, now that's really equal to Q. Remember the reaction quotient? Here it's not really a quotient, but it's the same thing. Sometimes Q is called IP for ion product, for solubility product problems. All right, so that's 1.6 times 10 to the negative 9. In the problem, it tells us that the KSP, the real known KSP, is 4.15 times 10 to the negative 9th. So it turns out then that this number is still smaller than that. So I have not hit my maximum product yet. So that means this equilibrium could go to the right because Q is too small. Remember, if Q is too small, I need to make more product. If Q is too big, I need to make more reactant. So Q is too small here. So it should go to, oh, wait a minute. Q is too small, so it should go to the right to hit our maximum solubility. So that means, will we see a precipitate? Well, the precipitate's on the left side. That's the solid. These are aqueous. So will we see a precipitate? Q is too small, so it should go to the right to make more of this stuff, and that is not the precipitate. The precipitate's over here. So we should not see a precipitate. So the answer would be no, we will not see a solid. Boom. And that's correct. All right, so that's all we did today in class. We did an introduction to colligative properties, like you to watch some movies. And colligative properties, again, are properties of solutions that are affected when you add a solute. And the practical application of that for you guys is freezing point depression and boiling point elevation. That's the primary place that you use it probably. Osmotic pressure too, but we won't get into that. So then the other thing we did today was talk about KSP. There are 3 kinds of KSP problems, and KSP is really just a specialty equilibrium application. So just one other way to talk about equilibrium constants. So three problems where you're given concentration, you find the KSP, or you're given the KSP finding solubility, or you're predicting precipitates. I did one of each. So you'll need to try those. And of course, there's all kinds of stuff on the internet if my explanation didn't do it for you. And this one, there is a written explanation on the actual handout, so it might be good to read that written explanation, which is wherever I put that. It's on the handout on this page right here. The written explanation, right? It's on this one. So that's the written explanation of predicting a precipitate. So it tells you what to do. All right. So that was the end of this video, and I'll post that right here where it says pending, right there. So in a few minutes that video will be in that position, and the quiz on this will be an extra credit quiz since we're right at the end of the year.